Finally, our translation properties associated with the Laplace transform. This will be important when we convert that S into j omega, which results in basically a Fourier transform, and that's important in terms of communications, where we translate the information centered at the origin to a new origin, basically into where the new origin is now centered at the carrier frequency. That's what we mean by the translation properties. But let's look at it here for the S domain case. So when we multiply it by an exponential, f of t, it says that our Fourier transform for this product is just the Laplace transform for this product is just f of s, where s is substituted for s plus alpha. So let's show that. So here's our expression. We apply our definition again from 0 to infinity, e to the minus alpha t f of t e to the minus st dt. Okay, combining these exponentials means that we add them at the exponents, and we just see that this is just an expression for the Fourier Laplace transform. Instead of s right here, we have s plus alpha. So this is just the Fourier Laplace transform. I get the Fourier and the Laplace transform interchangeably, but because the Fourier is a special case of the Laplace transform. Anyway, so Laplace transform, whenever you multiply by e to the minus alpha t, it translates the Fourier transform instead of f of s to s plus alpha. Okay, and in t-domain translation, let's say I delay my operation here in the time domain, likewise with the unit step, so it occurs at 0 infinity, we get f of s multiplied by e to the minus as a result of this time delay a associated here. So let's do that, applying the definition again. With the Laplace transform, everything is 0 until a. That's why it doesn't start at 0 now. So we can integrate from a to infinity now. So we got rid of this step function because we changed our integration limits. And then doing a change of variable where we substitute this t minus a for tau. And because of that, we take the derivative differential on both sides, d tau, since a is a constant, on the right side, then d tau is equal to dt. So we can substitute the dt for d tau, t minus a for tau, and then we have to substitute t here for t plus a. Okay? So t plus a right here. So we did the appropriate substitution. We replaced the t minus a for tau, dt with d tau, and the t in the exponent of this exponential for t plus a. Alright? Since e to the minus sa is not a function of d tau, we can pull it out of the integral, and now we recognize this expression is just a definition of f of s. Okay? So a time delay here corresponds to, of a corresponds to multiplying its Laplace transform by e to the minus as. Okay, so that's here's the tables of the summary. Let me go back, previous page. Okay, that we just talked about. Okay, so basic Laplace transformation properties. We have 3 columns. Here in the first column are properties, then the time column, and then the frequency column. Our independent variable is t, and our corresponding in the frequency domain or Laplace domain is in the s. The signal representation f of t, the corresponding frequency domain description of f of s. We have a unique operation here. We use linearity, integration. Again, the integration on a function is replaced by a 1 over s. Okay, differentiation. of a d dt is s times f of s minus the initial condition. Taking the derivative of this again is just an s squared, so that's associated with the second derivative, minus the initial conditions associated with my sf0 and the derivative of the function itself evaluated at 0. Alright, and you can extend it down to the third derivative, s cubed f of s minus s squared, etc. The S-domain translation, multiplying an exponential function, e to the minus alpha t in the at times f of t in a time domain, yields a frequency translation of s plus alpha in the frequency domain. On the other hand, called duality, okay, a time translation translates into multiplying its Laplace transform by e to the minus as. Alright, so here are some of the functions that we just looked at for the first here, and then we didn't look at the damped sinusoid, but you could we'll get to that. So the impulse is just a constant. Notice the impulse is very thin in the time domain, becomes very wide in the frequency domain, because it's a constant. We can look at the step function, u of t, we can replace it with 1 over s, multiplying by a ramp t, that's just 1 over s squared, and exponential, we just saw e to the minus alpha t corresponds to a 1 over s plus alpha in the Fourier transform domain, in the Laplace domain. A damp ramp is multiplying t, so notice you got a combination of t, so a t times u of t is just 1 over s squared, but since we're multiplying by an exponential, we replace the s with a s plus alpha squared. That's using the translation property. We saw that the sine has a sine beta t has a Laplace transform of beta, s squared plus beta squared, and we use this to calculate the cosine, and using the differentiation property to find its Laplace transform, which is just s divided by s squared plus beta squared. Alright, and notice you have a sine multiplied by exponential. So basically what we did here, we just take our sine, and wherever there's a s, we substitute s plus alpha, alright, using our translation property. So here's an s, the damping part of a sinusoid is s plus alpha squared plus beta squared here. Likewise, for a damped cosine, again we're multiplying by a damp exponential, that's damping, so it's a decaying exponential, and that's given by the cosine for this, the Laplace transform is this. So wherever there's a s, you substitute for s plus alpha, and that's what we just did here. Alright, so we covered some of the basic and important properties associated with the Laplace transforms, and we took a look at most of the important basic Laplace transform pairs.